So good morning, everyone. As you said, I'm Brian. I'm an engineer in the HPC team at HPC engineering team at Amazon Web Services. First, hello, greetings from Amazon. Amazon has actually been, you heard a bunch about cloud computing and HPC yesterday, and Amazon has actually been working on various HPC components kind of quietly for 8-9 years now. In June of 2010, we did our first top 500 run on our first 10 gig instance type. And at the time, 10 gigabit in a cloud computing environment was pretty impressive. In November of 2013, we released C3, which was the first cloud computing instance type where you were actually likely to be able to hit 10 gigabit bandwidth. We put a whole lot of effort into the network. We had some more of them laying around right before launch, and so we were able to hit number 64 on the top 500 list. Excuse me. We've since kind of increased the bandwidth to 25 gigabit a couple of years ago, and you'll see that kind of continue to rise over time across all the cloud providers. But about 2 years ago, about a year and a half ago, EC2 decided to build a software engineering team to, rather than just building the infrastructure for HPC, to start helping our customers with building the right infrastructure, software infrastructure to help them build the right environment and have the right software stack inside of an instance. And that's why I'm here. So just a little bit of background about HPC at Amazon. We don't have one way of doing pretty much anything. So we have a whole number of instance types that you can pick from. You can pick ones that are compute optimized, i.e. fast CPUs with about 2 gig of memory per hyperthread. You can pick ones with large local SSDs, GPUs, FPGAs, kind of across the board. We have a little of everything, and trying to fit the wide variety of workloads that customers are running in EC2. And those workloads are somewhat surprising. We have customers who are running fairly large weather codes in AWS and getting fairly reasonable results for the size of problems they're running. No one's running the very, very, very large runs, but the everyday I need to get work done runs are running quite well in AWS. Clemson did some fairly large machine learning runs late last year. At one point, their total cluster size, which is an interesting meaning in cloud computing, but kind of the total simultaneous instances they were running was about 1.1 million vCPUs, which is a little over 500,000 cores. For those who don't speak cloud, a vCPU in cloud computing is a hyperthread, essentially, in the Intel world. And aerospace. We have a couple of different customers running various aerospace applications, CFD applications. Again, not your 10,000 node hero runs, but the everyday 32, 64, 128 nodes, and quite happy. There are some fun engineering challenges. We like, at Amazon, we like Ethernet, and we like TCP as a result. The last time that HPC as a community really cared about TCP, that thing was being used for HPC. For those who are young, that's a PlayStation 3. And yes, at one point, we tried to use them for HPC. It was awesome. It had very small cores that you ran the operating system on, and it had gigabit Ethernet, and you needed multiple cores to drive that 1 gigabit. So it was a hard platform to program for, but it also had tuning parameters that looked very different than the Ethernet that we have in EC2 today, where we have 25 gigabit Ethernet. We have an Ethernet adapter and a software stack that's scalable out to 400 gigabit. You can't buy that today, but all the hardware interfaces can support out to that range. And you can drive that 25 gigabit out of one core fairly easily because Intel has turned the crank quite significantly since the PlayStation 3. But that PlayStation 3 is still what, say, OpenMPI's TCP transport engine is tuned for. And this has led to some interesting issues over the last couple of years. They always start with a quote like this: "My app is running slow," which is exactly what you want to hear if you're an HPC engineer, right? But we start digging in, and this particular app was quite slow when running under OpenMPI and MPI-CH, but fine when running under Intel MPI. And of course, the first thing you do as an engineer is try and get the application and quickly realize that you have no chance of pulling it apart, and so you resort to benchmarks. And we figured out that on our newest instance type, we could, excuse me, we couldn't drive 10 gigabit on a 10 gigabit instance type with OpenMPI or MPI-CH. And we start digging, and let's see if I can figure out. And these 3 lines of code right here are pretty much the only lines of code that OpenMPI and MPI-CH have in common. And what they're doing is setting the max size of the send and receive buffers on a TCP socket to 128 kilobytes, which, keep in mind, you want this to be a couple of round trips worth of bandwidth. And on our network, that was about 1 round trip. So if you had any delay in your packets, you were going to starve out your buffer size, and you weren't going to be able to send more traffic. Even worse, it turns out, since 2009, when we tuned all of those things, the Linux kernel TCP stack has gotten significantly more advanced, and more importantly, has started doing a lot of auto-tuning, which is great for most people. It's bad if you turn on, if you explicitly set these type of parameters, because the first thing Linux does is say, oh, the customer's trying to do something explicit. I'm going to turn off all my intelligence and go back to the 2009 slow stack. Again, not exactly what we want. And in this case, the solution was submit some code to OpenMPI. For me, that's pretty simple. Submit some code to MPI-CH. Again, pretty simple. Test a bunch of other codes to make sure they don't have something, a similar patch. But at this point, I've gone and looked at like 3 or 4 different middlewares and to figure out whether or not they have, they're setting tuning parameters for 2009 in 2018. And so it's a lot of duplicate work for us. The next problem we have is on our newest instance types, we have 25 gigabit networking, but they're a little odd in that a single TCP flow can only drive 10 gigabit. And MPI, the first thing any customer does when they use MPI on a new machine is they grab the OSU benchmarks and they run latency and bandwidth and message rate, right? And they all say, well, why can I only get 10 gigabit on my 25 gig instance type? And now we have to have a conversation with every customer, which I like talking to customers, but still talking to every single one about the same thing at some point gets a little old. OpenMPI has some code in it from that PlayStation day where you can drive multiple TCP links between any 2 pairs of processes, and now you see the 25 gig you'd expect to see. But again, so for OpenMPI, due to its design, that's actually fairly easy to implement. It was fix a couple of bugs in code that had bit rotted and were off and running. For MPI-CH, it's essentially re-implementing their TCP stack. That seems like a lot of work. Plus, for platform MPI, for Intel MPI, for GasNet, for Chapel, for all of these other things, we'd have to do the same thing. And so we started asking ourselves, is there a better way? And we started out, as you do in an engineering project, with some requirements. And the first requirement we had is that we couldn't dictate one way of doing things. We have a number of customers in AWS. They're all doing their own thing. This should be surprising to nobody in the HPC community. And even less surprising, they all have very strong opinions that their way is the right way. And so we have people using Intel MPI, using MPI-CH, using OpenMPI, using not many using OpenSHMEM, but a couple. UPC, Chapel, MXNet out of the machine learning. So we needed to support all these use cases. We wanted to future-proof in that today we're solely Ethernet and IP. We will probably always stay Ethernet, but doesn't mean that we have to have the exact same IP stack in TCP that we use today. And we have some interesting network behaviors because of what you get building a cloud network. Bill kind of touched on some of this yesterday in his keynote. So we wanted something that was future-proofed, that is, didn't have today's hardware design baked into it. And more importantly, we wanted this to be something that would work long-term, which means a healthy open source community. And we looked across kind of the spectrum of options, stick with TCP, just use UDP datagrams, Libfabric, Portals 4, because I came from Sandia, and so I had to look at Portals. UCX, using verbs directly. And when we really looked at it, the logical choice was to use Libfabric. It has a nice composability story. You can use, you can provide a very small core provider and use the utility providers to build on top of it, to build out the tag matching piece, the RDMA piece, the atomics piece, that you don't have to build all that in one go. You can do something very small, get your results, and iterate. And Amazon likes when we can get into that situation of get something to our customers, figure out how they're using it, and iterate on the important pieces. It has fairly wide adoption. If you look today, all the major MPIs have Libfabric support out of the box. GasNet has Libfabric support. Sandia OpenSHMEM has Libfabric support. Chapel either has or is working on Libfabric support. So out of the box, a lot of the things that our customers want have Libfabric support, and it's an interface that is fairly easy to grasp in terms of, okay, how do I take my middleware or my application and use Libfabric? It has the right application-driven semantics, right? So it's not what can the hardware do, and then I figure out how to write my application on top of that. It's what do I, as a middleware writer, want to do, right? I want tag matching, or I need RDMA, or I need these atomic semantics. And it has a healthy open source community, right? It has Intel, it has Cisco, it has a Cray, it has community that looks like it has, at least in our view from the outside, looks like it has a path to long-term success. And so, why we're interested? Because we have a number of applications and we need to make them faster. How we think we can help. The first one, we obviously have lots of computers at AWS, so testing is a natural way. We've been talking to Sean and synced up last night in detail, but we can test a number of the non-RDMA networks in our network. So the UDP provider, the TCP provider, RxD, all the different utility provider pieces, how they work over the various MPIs. We can run all these at the same time. So we think in about 15 minutes that we can do basically everything I talked about, run the fab tests, and get, so in a way that you could use in CI, similar to how Howard set up the Cray tests for you guys for Libfabric today. We've been working a little bit behind the scenes on debugging RxD over UDP, and we'll continue there and continue working with Intel in accelerating that, making it faster. And then the other piece that Sean's has said Intel's working on is multi-rail. He'll talk about that, I think, more next. Due to the whole multiple stream TCP thing we have in our network, we're very interested in making multi-rail work with TCP and UDP providers. So that customers just out of the box naturally get the full bandwidth that they kind of expect on their benchmarks. Even though for applications they already get what they want, they like seeing the benchmarks have kind of the right answer. So that's all I had in terms of what we're interested in doing, why we're interested in it, and why we found Libfabric was the right semantic or the right way forward for us. So welcome to take, or happy to take questions. Yeah.
I was surprised to hear you say that TCP/IP is limited to 10 gigabits of data.
So a given TCP flow. So it's a 25 gig instance type. You can drive, if you have 3 TCP flows, you can drive 25 gig. Each one would be limited to 10. And it's just an artifact of how our network works. So the question was why we have a 10 gigabit limit, and so. Any other questions?
Can you tell us why your network only limits to 10 gig?
Can you please come up with the mic for the question?
The question was why we're limited to 10 gig. It's artifact of a couple of pieces of our network design. That's.
How long do you guarantee 10 gigabit flows?
It depends on the instance type. The question was how long do you guarantee 10 gigabit flows? And the answer is it depends on the instance type. We have some instances that have what we call burst, where you can run at 10 gigabit for some duration, and then your baseline is lower. And then on our largest instance sizes, the answer is all day long. So that is, as usual, all kinds of network impacts can occur, but generally there's nothing we're doing to try and stop you from driving 10 gig all day long.
So primarily that would be in placement groups with the larger machines?
So placement group, yes. The question was, the follow-up was if that's in placement groups on larger machines, and the answer is so placement groups are an artifact of AWS is quite large, and placement groups are a way of bringing down the ceiling on your worst case latency between any 2 instances. And yes, that's your best chance for getting the highest bandwidth because your latency is lower and your kind of network distances are lower.
Can you comment at all about?
Since you have questions, can you please come up with the mic? Because we are recording the session.
Can you comment at all about like the number of workloads, the type of workloads, the sizes and things like that people are currently running, and what you're expected to be able to support, or what you project you're going to be able or be running in terms of HPC workloads in the future?
So then, on the kind of treating them each individually, I have been surprised at the breadth of workloads. I touched on a couple. Weather is always interesting because it generally has semantics kind of outside of the standard BSP, lots of bandwidth, who cares about latency? There's lots of fluid dynamics, whether it's the aerospace that I mentioned, cars. So lots of fluid flow, lots of ANSYS mechanical, and similar type of applications. Machine learning and a little bit of the computational chemistry, although most of what I've seen there hasn't been scale really horizontally. I do know a couple of customers who are running relatively large lamps runs. So that's kind of the breadth. Truthfully, there's been very few things where customers have come and said, this workload just doesn't work. There have been places where maybe they don't like the scaling as much as their on-premise InfiniBand cluster, but what they do like is hey, the cluster's got a queue that's 3 weeks long. I need to get this result for a paper in the next week. The fact that it ran a little slow is fine because I was able to build the cluster in 20 minutes and get my nodes in 20 minutes, get them set up and run my application and get the paper written, and that's what I care about, right? The job sizes are still on for this community, kind of the lower end. So lots of 8, 16, 32 nodes. Some customers, particularly in the more BSP style applications that aren't as latency sensitive, are 64, 128 nodes. And there was a third question there was a third part to that I've forgotten.
Well, and how much do you see this growing?
Yeah, so growth, yeah. I don't think things I probably shouldn't say in a video that's going on the internet, but I think it's safe to say we're not going after the high end, the high end of what Cray can do, the 10,000 node hero runs. I do think we can get a couple of more turns of the crank in job size with relatively ease with where we think our roadmap is going and where Intel's roadmap is going. So getting that. I would really like to get to that 1,000 node personally, because I think that captures a good chunk of the kind of commercial HPC market.
Do you have traditional hotspot problems like congestion management, quality service, things like that? And if so, are you getting enough control through Libfabric to be able to manage those issues?
Yeah, so today we're using TCP for congestion control, and so we don't see a lot of the pieces that maybe you'd have to do with Libfabric that you might want to do on an InfiniBand or a Cray network. And our network, Bill had some slides of some of our competitors' networks up yesterday. We don't talk much about what our network looks like. I will say it wouldn't look surprising to anyone in this room other than its sheer size. And so one of the things that's surprising to customers when they come is and start doing HPC in AWS for the first time is we don't have I'd like a rack. I'd like however many nodes in what we call a placement group, which is a fairly sizable network domain. And so in a lot of ways, a lot of the hotspotting you see in HPC networks on premise where there's an application using a significant portion of the entire network don't happen with our network design just because of scale. It's one of the places where you have to either be really smart or really, really big. Both is best, but when you have the really, really big, you don't have to be quite as smart. So we haven't run into the problems yet, so I can't answer the question that you were probably really interested in. Any other questions? All right, thank you.